there's all my work for that one in case you just need to see all of that. But the graph is the amount of people that are moving into the line. All right, they're arriving at the ride throughout the day, so they're going to wait in line. That's what this graph is about, and they're moving onto the ride at a rate of 800 people per hour. So part A just says how many people arrive at the ride. You don't care how many people are already there. You just want to know how many arrived in between 0 and 3, and that's what this graph of R is. So you're going to integrate R in between 0 and 3. And so when you got to integrate that equation up there, that graph up there, that's going to be the area in between 0 and 3. Now, what I did when I saw in between 0 and 3, I drew in two trapezoids. I saw a trapezoid right here, and then another trapezoid. You're going from 0 to 3, another trapezoid right here. So when I'm finding the area of this one, here's the area for the trapezoid. I did base 1 plus base 2 divided by 2 times it by the height. So I did 1,000 plus 1,200 divided by 2 times it by the height, which is 2. That's how I came up with that. And then the second trapezoid, I did this base. So I did 1,200 plus the 800 divided by 2. Those are my two bases. And then I times it by the height, which is equal to 1. So I got that right there. And then I believe this was a calculator problem there. So you're just going to get 3,200 people. Now, letter B says, is the number of people waiting in line to get on the ride increasing or decreasing between 2 and 3? All right, so I guess what I'm looking at here, this is people per hour. How many people are entering the line at a certain time? So like at t equals 2, 1,200 people per hour are entering that line. At t equals 3, 800 people per hour are entering that line. At t equals 2.5, you're up there at like 900 something, 1,000 people entering the line, okay? Now, so it just says in between 2 and 3, which is this little line segment right here. Now, what we gotta notice right here that people are moving onto the ride at a rate of 800 people per hour. So if 800 people go on the ride, then I just got to think about how many people entered the line, how many new people arrived and waited in line there. Is it bigger than 800 or smaller than 800? Did that line get bigger or did that line decrease right there? So if you notice it between 2 and 3, again, this is the graph of how many people arrived to get in line. In between 2 and 3, this line segment is bigger than 800. So the amount of people that arrived in line is greater than the number of people that left the line to get on the ride. So onto the ride is 800 people per hour, but in between 2 and 3 who are arriving at the ride, getting into the line is bigger than 800. So that means that line is getting bigger. So for example, at like 2 point something, 1,000 people got in line, like 800 people got into the ride, but then 1,000 got into the line again. So that means that line increased by a couple hundred more people right there. So since the R of T, the getting into the line is bigger than the 800, it's going faster than what they're leaving the line going into the ride, the number of people waiting in line is going to be increasing. Letter C says, what time is the line for the ride the longest? How many people are in the line at that time? So we want to maximize something, right? So what I did, I came up with a line equation, and here I'm going to take into account everything. How many people are already there? How many people left to get onto the ride? And how many people are entering that line? So the initial amount of people, it tells us we're at 700 people in line at the beginning. So I started with the initial amount that was already there, and then they're leaving the line, getting onto the ride. So that means you're going to subtract out those people at a rate of 800 people per hour. That's what's giving us right there. They're leaving the line. So we're subtracting them out. They're gone. They're going onto the ride at 800 people per hour. And then your integral between 0 and some time period, when you integrate the R, you're integrating this R. That's going to give us the total number of people that arrived throughout the day. Like letter A, you figured out that was 3,200 in between 0 and 3. Now we're going to figure out 0 between what time period. So there's like our equation for our line. When I want to find a critical number here, or trying to find a possible max or min, you take the derivative and set that equal to 0. So the derivative of that is 0. The derivative of that is a negative 800. The derivative of the inside of that integral is R of T. And then when I just saw this equation, I just add 800 to both sides. I want to know when is the R equal to 800. Again, the graph above is your R. So we're going to use the graph here. I want to know when is the R equal to 800. So that's right here. When that crosses 800, boom, that T is equal to 3. So that's going to be like a max. And then when you want to find out how many people are in the line at that time, take that 3 and plug that into that integral right there. So we're going to go 700 minus 800 times 3. You plug in the 3 there, in there. So we'll go 700 minus 800 times 3, and then the 0 to 3, do the math. Now with the actually, you already got this answer from part A, that 3,200. So you go 700 minus the 2,400 plus the 3,200 to get that 1,500 total people. I think that's all we need for the justification. It crossed my mind to do an XY chart as well. So I kind of just, I don't know if we need a sums problem. Usually we give them like a closed interval and it's an absolute extreme problem. But I do know if you check the endpoints, the hours of operations are in between 0 and 8. At 8, there are 0 people in the line. It's not like there's, you know, when the park closes, there ain't going to be anybody there. So that's not going to be a maximum number of people waiting. And at 0, it told us there were only 700. So when you got the 3, that was your 1,500. Another reason you can get that 3 is we said in between 2 and 3, the getting in line rate was higher than the entering the ride rate. So the line was increasing. And then when you go on the other side at this stuff is all below the 800 rate of people getting on the line. So that means it switches to decreasing. So if your function changed from increasing to decreasing at that t equals 3, the total line function, then that's going to be like a maximum right there. But if that equation made sense where I just took the derivative, set it equal to 0, looked at the graph, that's what you need there. You need the t equals 3, we need the 1,500 people. And then letter D just says write an equation. I don't have to solve it. Just write an equation who gives a solution for the earliest time at which there is no longer a line for the ride. So if there's no longer a line, that means this total line equation that we got in part C, that means you just take that total line equation and set that equal to 0. I guess going up here, I could have switched that letter. I don't think they'll be too picky about that, but if you're really worried about it, always make that like your t, like the variable that you want, and then you could just switch that to any letter you want there. Because when you integrate that, you'll get something, but then you'll plug in the t, you'll plug in the 0, and then you have everything in t's again right there. So that's just a little technicality when you're setting up those equations there. We might as well just kind of practice switching that other way. But again, it says write an equation, so you got to take it and then set it equal to 0, and then we're done there. Snowflakes.